last video in this series we're going to look at for vectors is going to be projections and the vector component. So let's start by defining what a projection is. Okay, so vector components are basically breaking up a vector into the summons. Okay, so if we add two vectors together, so for instance, if I had 1 comma 2 plus 3 comma 4, that would be equal to 4 comma 6. And what if I wanted to break it up back into 1, 2 plus 3, 4? All right. Well, we can do that by finding something called the vector projection. Okay. And in fact, what we're going to do is we're going to find a vector that's going to basically have the same magnitude, if you would, as the original vector, but we're just going to cast it onto another vector v. Okay, so basically, if we have u and we want to project that onto a vector v, we're just going to take this and we're just going to drop it down, okay, onto v. Okay, and so this whole thing w1 is going to be the projection. Okay, so now we define that as the projection of u onto v. Okay, so that's all we're really doing. We're just taking something and we're taking a vector and we're laying it on top of another vector so that it goes in the exact same direction, but it has the magnitude of the original vector. Right now, this animal W2 is going to be orthogonal to W1. Okay, which is the projection of U onto V. Okay, I'm sorry, the other way around. U onto V. I know it's when you write it, it should be V first and then U. Okay. But that's what we're looking at. We're trying to find W1 and W2 such that W1 and W2 are orthogonal and W1 is the projection of U onto V. Okay. And you can clearly see how this works. Okay. So let's figure out how we're going to do that. Okay. So U is the sum. Okay. So if this is U, okay, or the vector U, then this might be like W1 and W2. Okay. And I know that they're not. Okay. But that's how you would go about getting those. Okay. And W1 and W2 are orthogonal. Okay. To the original vector V. Okay. So let's go ahead and find a formula for this. So again, W1 is the projection of U1 to V, and the formula is right down here. U dot V divided by magnitude of V squared divided or multiply that by V. Okay. To get, and this would be the same thing as W1. Now, to get W2, remember that W1 plus W2 is U. So to find W2, which would be an orthogonal vector to both V and the projection, W1 would be equal to U minus W1. Okay, and again, W1 is the projection of U onto V. Okay, all right, so I'm going to work an example and I'm going to show you all the various vectors for one example, and then I'm just going to compute the projection as well as the orthogonal component. All right, so let's say we have these two vectors. Let's say we have 3, 2 and 3, 4. All right, and what I want to do is I want to project U onto V. Okay, so I'm going to find that vector, and then I'm going to decompose into two vectors. All right, so let me start just by plotting those two vectors. And I kept it simple just so that way, it's easy for us to graph. Okay, so we have 3, 2. So this is going to be our vector U. Right? And then we have the vector V, which is 3, 4. All right, I'm going to draw that a different color so that way, I'm going to try to draw them all in different colors so that way. Okay. All right. And so what we want to do is we want to project U onto V. So basically, we're just going to find a vector that goes in this direction and it's going to lay on top of V. Okay. So again, this is our vector V and our vector U is going to be the one in blue. All right. So let's find it. Our formula, okay, remember, projection of U onto V is U dot V magnitude V square, and we're going to multiply that by V. Okay, so erase this and make them actually look like, sometimes I just write too fast. That's not a square. We're going to multiply all of that by V. All right, so let's find U dot V first, which is easy. Okay, so that's going to be 3 times 3 plus 2 times 4, and that's going to end up being 15. Okay, or nice and easy, 9 plus 6. Magnitude of v, again, really easy. Square root of 3 squared plus 4 squared. We've seen this many, many times in the course, right? 3, 4, 5. And that's just going to be 9 plus 16, which is root 25, which is 5. Okay. So now for us to find the projection, so the projection of u onto v, well, that's going to be equal to 15, which is u dot v over 5. Okay, so that's, and we have to square that. Okay. And then we're going to multiply that by 3 comma 4. Okay. Now we know that 15 over 5 squared is going to be 15 over 25, or that's going to end up being 3/5. So we have 3/5 of 3 comma 4. And if we distribute that 3/5 through, that's going to end up being 9/5 comma 12/5. Okay, so that's our projection. All right. And if I wanted to write that as a decimal, which might be helpful, all right, we know 9 over 5 is 1.8, 12 over 5 is 2.4. Okay. Now let me plot this value. Okay, 1.8 comma 2.4. And remember, this is W1, which is the same thing as the projection. Okay. So I'm going to plot that in a different color so that way you can see it. And let me zoom in just a little bit. Okay. Or just a lot. And we have 1.8, 2.4. So 1.8, 2.4 is going to probably be like somewhere up here. Okay, I know it's not really good. Okay, but it should be right there. And so this should be W1, which is the projection. Okay, the projection of U onto V should lie somewhere on V, and it should have the same magnitude as U does. Okay, so and if you don't trust that, you can find the magnitude of both U and the projection. Right? Now, one last thing is that it asks us to be able to find the decompose U into two vectors, U1 and U2, where U1 is parallel to V and U2 is orthogonal to V. Okay, well, the good news is U1 is just going to be the same thing as the projection. Okay, so this is part B. U1 is the same as the projection of U onto V, which we said was 9/5 comma 12/5. To find the other part, we're just going to subtract this vector from U. Okay, so U2 is going to be equal to U minus U1. Or in this case, remember U was 3 comma 2. And we're going to subtract from that 9/5 comma 12/5. Okay. Now, if I subtract that, okay, if I get a common denominator, okay, that's going to be 15/5 and then 10/5 minus 9/5 comma 12/5, or that's going to be 6/5 comma negative 2/5. Okay. And that's going to be the orthogonal vector. Okay, now as a decimal, that's 1.2 comma negative 0.4. All right, so let's graph that finally and see what happens with that. Okay, and remember, my graphs aren't all that accurate. Okay, so let me zoom in one more time. Let me find one last color that we can use. Probably red's good. All right, we can use this violet, I suppose, but what's this color here? Pastel pink, even better. All right, so we had the vector 6/5, which is 1.2, and then negative 0.4. So probably like right down here somewhere. Okay, so now this is our vector W2. And what I want you to notice, good thing I didn't use red, is that W1 and W2 are indeed orthogonal, at least by our graph. Okay, if we don't trust it, we could certainly find the dot product. Okay, and that would suggest that it's going to be orthogonal. Okay, so that's what all this stuff is all about. Okay, so hopefully that makes a little bit of sense as to what we're finding. Okay. Now, in later courses, you're going to figure out what the dot product's actually for. Okay. We can use it to be able to find work and some other applications as well. All right, let's take a look at one last example of being able to find the projection of u on the v. All right, so remember our formula. Okay, so our projection of u on the v, u dot v divided by magnitude v square times v. Right? So I was about to write the vector for that. So let's find u dot v first. Okay, so u dot v is going to be equal to 1 times -2, right? And then plus 3 times 5, which that's just going to work out to be 13. Okay, I think everybody can see that we're going to have -2 plus 15, nice and easy. Okay, next thing we're going to do is we are going to find the magnitude of v. Okay, magnitude of v is going to be -2 square plus 5 square, that's square root of 19. So if we throw this into our formula right here, u dot v is 13. We have the magnitude squared, so square root of 19 squared, right? So let me make those look like real numbers as opposed to somebody just trying to draw on a computer screen. And then we're going to multiply that by v, which happens to be, I'm just going to put it into the component form instead of a linear combination, -2, 5, all right? And then we know that the square and the square root are going to cancel each other out. And so if I multiply through by 13, this is going to be -26/19, comma, 5 times 13 should give us 65/19. Okay, so this is the projection, and it's the same thing as W1. Okay, so this is our W1, which is also the projection of U on to V. All right, now the last part is finding part B. Okay, and so for part B, we know that U1, okay, so if we go back up and answer what it's asking, U1 is parallel to V. Okay, so that means that U1 is going to be -26/19, comma, 65/19. Okay, so that's easy enough. We just find the projection and that's what it is. To find U2, that's going to be U minus U1 in this case. Okay, so we're just going to subtract those out and we might have to get a common denominator. Oh well. All right, so we said that U was going to be -2, 5. And minus the vector -26/19, comma, 65/19. Okay. And then here, what we can do is we can just get a common denominator for this. Okay, so this is going to be negative. If we get a common denominator of 19, 2 times 19 is 38/19. Okay. 5 times 19, that should give us 135. All right, so yeah, I think that's, or I'm sorry, not 135. It's 45, and then that's going to be 95. Okay, so that's going to be 95/19, and we're going to subtract from that -26/19, comma, 65/19. All right, and of course you could do this in your calculator. I just don't have one that's as fast as what I can do it with. All right, so this is going to end up being plus 26. So -38 plus 26 is going to be a -12/19. And then 95 minus 65 is going to give us 30/19. Right? Of course, you can always check this by taking the dot product and seeing if the dot product between U1 as well as U2, because remember they're supposed to be orthogonal, should be 0. Okay. So if you dotted these two together, okay, should end up being 0 for those. Okay. All right. So I think that's everything that we need to be able to do these sorts of problems with respect to the dot product. Okay. And so when we're going through and doing these sorts of things, we want to make sure that we remember the definition of our dot product, and then also the various sorts of applications that we've looked at so far with respect to dot product.